And the answer is that finding a good overestimate is really a big part of our life. It's the most frustrating one sometimes. And there are sort of various algorithms in order to find to construct good overestimates from a bit of numerical data, in a sense. There are sort of theory arguments for particular cases of where you think you find a good approximation of your theory and use that for g of x. And then there is some common knowledge, for example, about these particular things, like these splitting functions down here, this p of z, where, given that people have been doing these things for half a century almost, there is some trade knowledge of how to do this relatively efficiently. But it's still part of a very large part of our workflow. And whenever there's a new algorithm to find good overestimates, or that maybe makes it a bit more independent of overestimates, we get really excited. So maybe we'll actually hear some kind of algorithms that says something about new algorithms further down the road. For example, Frank has invented a very nice new algorithm to be a bit more independent of overestimates when it comes to this radiation cascade. All right, and moving on to lecture 2. So lecture 2 is supposed to be now about phase space and phase space sampling. This is one of the big parts of how to arrive at calculating a average observable, so kind of calculating what a measurement should look like. Then we move on to how to sort of assemble a hard scattering section. So this is the scattering, the part of the event generation where the largest momentum transfer will occur. And then towards the end, we'll have a very short excursion of how we think we can factorize these hard scattering cross sections into smaller bits that we can then approximate and then use in order to distribute these few particles, or these few quantum numbers that we have in hard scattering, over a larger set of particles that will form the radiation cascade. But let's start with phase space. Going back to physics a bit again, the measurement of an observable is given by this formula. So you integrate your test function, which is the value of observable, against your probability distribution, which is the differential cross section over the whole phase space. So what you would have to worry about is you want to sample phase space points, phi n, and you want to calculate the differential cross section. And evaluating the observable is, in a sense, you can hopefully factorize a bit. So the challenging task really is to find a sample phase space point in such a way that the weight of these phase space points is fluctuating only mildly. So that, just like in this kind of inversion sample, or sort of important sampling methods that we just discussed a couple of minutes ago, you want to try to sample these phase space points with a distribution that is as close as possible to the differential cross section already, such that you retain you are efficient in sampling those as well, and don't throw away a lot of resources. In order to do that, well, when we sample phase space, we need to avoid large fluctuations. We need to avoid an excessive projection rate. The way how to do this is to take this big integral, which is really high dimensional, phase space integral given here, and factorize it into smaller steps that we can individually solve more easily. And then we reassemble the smaller steps into a bigger whole. So it's again divide and conquer, like almost all of the things in the Monte Carlo. So this phase space integral, right, integral over 3 components of momenta for every particle, and enforcing momentum conservation overall gives you 3n minus 4 dimensions. So if you have 100 particles in the game, you have 300 integration dimensions, which is a bit high. and happens quite regularly, for example, at the LHC. The way how you factorize this thing is by introducing pseudoparticles that you write into the phase space and that you then integrate over. So you can factorize the phase space integration of these n particles into an integration over n minus m particles, and the integration over m particles, and one additional integration over the sum of the momentum squared of this pseudoparticle in between. This is effectively just saying that you take this n-dimensional integral, you introduce an auxiliary integration, which contains you add an auxiliary integration over this intermediate particle that comes with a additional delta function in order to make sure that you have momentum conservation overall. And then you rewrite these smaller bits in convenient ways. And you try to do that until you have only simple integrations left, say 2-body decays, 3-body decays, for which you can write down the answer or write down how you do the integration on paper. So for 2-body decays, you know that in the rest frame of the decay, particles are back to back. So you only really need to create one particle, meaning 3 degrees of freedom. And these 3 degrees of freedom are probably something like the length of a vector and length of the vector, an angle of and 2 angles for the vectors. For 3-body decays, you can invoke other things that have 3 integration dimensions that are typically challenging to solve without clever parameterization, like the spinning of a spinning object will be able to rotate in 3 dimensions, and you express the 3 dimensions, for example, in Euler angles in order to make the integration more tractable. You would do the same for 3-particle phase space. You can write that in terms of invariant masses and Euler angles. So once you find a clever parameterization for that, then you have really factorized your phase space integration into simple things that you can then use in order to create efficiently these large dimensional phase integration points in the integration region. For example, one of the clever parameterizations, really clever parameterizations, kind of need to know a bit about the integrand that you're integrating over. So they need a bit of knowledge on the differential cross-section. Let's, for example, say your differential cross-section looks like this. This is the cross-section in terms of center of mass energy of an electron-positron pair annihilating into hadrons. And what you see is that there are sort of tons of features in here. So first you see that kind of a flat overestimate here would be a bad way of sampling, because there's many orders of magnitude between this peak, this valley here, and these peaks up here. But you luckily also know that some of these things, like the Z boson here, they actually come from a resonance decay. And a resonance decay means that there is a structure in your differential cross-section that looks like a Breit-Wigner distribution, something that's proportional to the ratio to invariant mass of the decay products minus the vector, the resonance mass, plus something that's proportional to the width of the resonance. So if you know that, then there might be a way to do a to sort of write down a 2-particle phase space integral, or the sampling of a 2-particle phase space integral that includes these things. How do you do this? Well, you do inversion sampling again. So you take this simple function. This is an overestimate maybe now of your real function out here. You integrate it between the maximum and minimal values of the thing that you want to generate. Say, for example, the invariant mass of this peak here, of this resonance. This gives you these Arcus tangens functions. And luckily, although this looks complicated, this is actually invertible quite easily. So if you throw a random number R between 0 and 1, and you set your value of S to the inverted cumulative function evaluated between S max and S. And with this, what you've now done is, instead of having to sample randomly points here, you actually sample points where they matter most, really in this peak of the integral over here. And you've used knowledge of your differential cross-section in order to make your sampling more efficient. So this is something that we try to do as much as possible. If we know the integrals, we try to use inversion sampling as much as possible because it's the most efficient way of doing things. However, just like in this case here, right, there are tons of these types of resonance. Right? There's a Z resonance, but there's also a phi resonance and an omega resonance and so on here. There's a J psi resonance here, a very small one, very narrow. So we can't use inversion sampling with only a single width and only a single mass parameter in order to get a good, efficient sampling of this peak and an efficient sampling of this and the other peaks. How do we solve this? So we already know from data that our integrand has these tons of peaks, all of these relatively simple peaks. The way how to do this is actually to split up the integral region into smaller bits and use overestimates in these individual bits. So this is called multi-channel sampling. The most simple example, I think, is probably when you think of, say, a Z boson decaying into a pair of quarks, Q bar, and a gluon. In this case, there are two Feynman diagrams. One of them where the gluon attaches to the quark, the other one where the gluon attaches to the antiquark. And of course, there's interference of these two. In this case, in the first case, where the gluon attaches to the quark, this part of the transition amplitude is enhanced when the invariant mass of this particle pair goes to 0. And we'll discuss that later on a bit. And Dave will discuss that, I guess, profusely in his lectures. And the second part here, where the gluon attaches to the antiquark, is enhanced, where these two momenta, the invariant mass of these two momenta squared, becomes very, very small. So there are two competing pieces of our transition amplitude that have relatively simple structure that we would like to sample from in order to get a good and efficient algorithm. So what we do is we design two overestimates. So a G1 for this here and a G2 for where the gluon attaches to the antiquark. Then we choose an index, 1 or 2, according to the discrete transformation method, meaning just we integrate these functions of all their possible values. That gives us a number, and that number is that and that large for both cases, and we pick according to what is this overall probability. Now we've chosen a index. Then we draw the random variable x according to the overestimate for the index that we've chosen, say according to G1 or G2. Overall, if you do this very, very often, that means that x is now distributed. So the population of the sample is now distributed according to G1 plus G2. The only thing that we now need to do is we need to adjust this overall population in order to recover our sort of more complicated function f. And you do that by, again, using rejection sampling. So you draw a random number between another random number, draw lots of random numbers here, draw another random number between 0 and 1, and you accept kind of the pair of index and value, index I and value x, if for that pair f of x over g of x plus g1 of x plus g2 of x is smaller than the random number. Else you reject and start. Again, this is very, very heavily used, both in the generation of phase spit, but also, for example, in parton showers where there are multiple different structures in the matrix element that you might want to sample from through inversion sampling. Again, the idea here is to try to use inversion sampling with good overestimates G as much as possible, because that's the most efficient algorithm that we have in order to distribute things. An exercise that you could think about is you could draw x from the distribution 1 over square root of x times 1 minus x. So this has two types of enhancements, one at x goes to 0 and one at x goes to 1. And you can use two integration channels in order to get an efficient way of doing this. And you can prove that maybe if you want to, this algorithm that is on this slide here will actually be able to handle this quite nicely. Okay, so this all looks very good. So why don't we just go home and do this? We devise our own overestimates, and this is how we'll spend our waking days until a kingdom come. Well, quite often, however, analytic knowledge of the differential cross-section is hard to come by. These differential cross-sections, although we might be able to write them down, might have very, very complex structures that are difficult to sort of isolate individually, and they might even have overlapping enhancement regions. So quite often, finding a good overestimate is not immediately viable. Another way of looking at inversion sampling, however, is to generate random variables in integration regions where they really matter most, right? You try to generate random variables or generate phase space points, mostly in the regions where you have resonances, and not really in the tails where you don't have resonances. This is, in a sense, the construction principle of something that is very powerful called stratified sampling, which is really at the core of most of phase space integration. Here, the idea is you make very small, you divide your integration region into very small subregions, call them bins. And in each of these subregions, you simply say your overestimate is indeed a uniform distribution with maximum value of the function in this small bin. Then your task is to try to put more of these kind of smaller bins in the regions where the variance of f is large, so that these bins, that the region of the resonance gets more populated simply because you have more bins there. This is the construction principle of Vegas. And an example, for example, is here, that you have a function that is initially rapidly decreasing, then it develops a resonance and then flattens off again. So in these flat regions here, you might put 1 or 2 bins. Around the resonance region, you put a lot of bins. And maybe here with the initial descent, you put a couple of more bins in order to sample from that. The way how you do this is you evaluate the function very, very often, initially, and try to adjust, given how your evaluations of that function, you try to adjust the spacing of these different bins in order to minimize the variance within these individual bins. So Vegas, the standard algorithm to generate phase space, really needs to learn good integration grids by sort of a warm-up stage where you actually train the integration grids. Coming to training, of course, there are also modern methods that allow phase space integration using neural nets or using more advanced machine learning techniques. So Vegas, in principle, is a machine learning technique, but there are more fine-grained ones that use deep nets that can be helpful in order to find a good way of sort of fractioning phase space in order to make this work nicely. Let me look at the time. Okay. So once now we have a phase space point, it's time to evaluate the differential cross-section. So the differential cross-section, I've not written down what it actually looks like an integral over the distribution of the particles interacting in the beam, a flux factor kind of telling you what is the velocity of the initial particles compared to the velocity of the beam, and a transition probability, which is given by a matrix element, transition matrix element squared. This distribution of particles in the interacting beams, that's typically something that Monte Carlo event generators do not themselves create, but that is taken from the outside, let's say, for example, from a parameterized measurement. If you, for example, collide protons, then these distributions would be the distribution of partons inside of the protons, the PDFs, as measured and fit in previous experiments. So for the most part, the task of Monte Carlo event generators is to evaluate, for the hard scattering itself, the transition probability m squared. This relies on perturbative quantum field theory methods, meaning that if you would do that on pen and paper, what you do is you'd calculate Feynman diagrams. You use then completeness relations in order to simplify the squared expressions. And then once you have that, you start summing and averaging over external quantum numbers that you don't observe, for example, say, let's helicity, color, and so on. That's easy enough to do on paper. Clearly, doing calculations on paper becomes relatively tedious once you have a complex final state. So in real life, we use somewhat different approach, which is to first fix the sum of the quantum numbers of the final state, for example, the helicity and color, then calculate the relevant Feynman diagrams for this fixed set, and then square only afterwards. This gives very much sort of less complicated intermediate expressions, because they're only valid for fixed helicity and fixed color and so on. So, and the squaring also gives a much better scaling, because you don't have superfluous diagrams that you calculate in intermediate steps. What you then do is then you have to sort of sum and average over all helicities simply by Monte Carlo method. So you pick helicities randomly, and you pick that often enough, and you calculate for these different helicities. For example, you calculate the matrix element. So again, you use Monte Carlo methods to make your life a bit easier. Instead of calculating Feynman diagrams and then only at the end summing, you sort of fix the point, the term in the sum that you want to calculate. You calculate that, and then you do a Monte Carlo sum, just like we had to do a Monte Carlo sum in order to get the average of a function. Same principle. Okay, so we'll now go through a couple of hoops in order to see what can we do in order to make our life easier when calculating these transition matrix elements. And first is color. Color is quote unquote easy because it's not a dynamical quantum number, meaning the color factors or the color algebra of quantum field or of quantum chromodynamics does not depend on the momenta of the partons themselves. It's a algebraic it's an algebraic expression. So what you can do is you can strip QCD amplitudes of their color factors, off in a sense that the product of all the color matrices that you would have to assemble before doing an evaluation of the kinematic part of the matrix element squared. For example, for an n-gluon amplitude, you can split off sort of the trace of the all the n-gluon of the matrices, or the sort of adjoint matrices that you would have when you sort of attach a gluon to a leg. You sort of factor that trace off from the kinematic part of the matrix element. Similarly, you can rewrite a gluon in terms of a particular basis that you choose. For example, say the gluon is, you express adjoint generators of QCD in terms of the fundamental generators of QCD, these lambdas here, and you factor that off. And there are many more ways of doing this. Many ways of doing this, what is called color ordering. So color ordering means you strip off the color matrices from the actual transition matrix element so that you can calculate the transition matrix element independent of the color. So that means you can pre-calculate these color factors, store them somewhere, and then when you calculate M, you try to recycle your calculation of M for a particular set of momenta as much as possible. Alternatively, you can go all in and actually fix color at each vertex that you have in your matrix element by random sampling and then sample over this. This is called color dressing. So, for example, done in the Sherpa generator, and can be very, very efficient at high multiplicity. So instead of like doing this color ordering, simply assigning values and then sampling these values in a random fashion. Again, using the power of Monte Carlo. Once color is stripped off, then we need to calculate these kinematical parts of the amplitude. And that is typically done from the outside inwards. So if you look at matrix element generators like MADGAR, COMIX, AlpGen, for example, as well, you really calculate the matrix element from the outside inwards. So you start with saying, well, you know, for example, that you have a particle that decays and produces 4 particles. You assign helicities to these 4 particles first. And then you start contracting the wave function or spinors of these of subsets of these 4 particles in a recursive fashion. So for example, you start contracting 1 and 2 into a new particle that you call 1, 2. And then you contract that new particle 1, 2 with a particle 3 into particle 1 to 3. That particle that particle 1 to 3, you might then contract with a particle 4 to produce particle 1 to 3, 4, which you then finally contract with the spinor or wave function or polarization vector of this decay particle here. The good thing about this is that this is a very efficient way of doing calculations because you can recycle a lot. So typically when you write down a Feynman diagram, right, you sort of say, okay, I will go against the fermion flow, I contract all the gamma matrices and so on and so on. Forget about this. Here, what you do is you take everything from the outside and then you contract things in all possible ways in order to construct all possible diagrams. So, for example, you can take your sort of contraction of particles 1, 2 into particle 1, 2, and the contraction of particles 3 and 4 into 3, 4, to contract these 2 kind of branches directly into a particle 1, 2, 3, 4, which you then contract with the resonance. So that means here that you've actually sort of created a new type of diagram. This is the basis of helicity amplitudes methods, which are used throughout the event generators, and is a whole field of research. Is finding the most efficient way of doing this recursion is quite challenging. But I think by now, at least for tree-level matrix elements, this is more or less solved since 10 years or so. However, looking at tree-level matrix elements on their own for multiple particles is actually quite questionable. And that is because you have to be a bit careful about their singularity structures. Put another way, if you count the number of coupling powers or number of particles in the final state, then you see that if you increase multiplicity in the final state, the number of particles, you also increase the number of couplings, but only increasing the number of particles in the final state is not the only way of increasing the coupling power. There is also a way of increasing the coupling power by simply producing virtual particles. And it's because of these virtual particles that, it's these virtual particles that actually make the cross-section well-defined at higher orders. What happens is that at tree level, you will encounter infrared singularities when you radiate, when you sort of produce further particles. And that is because some of these intermediate propagators that you have in these radiative diagrams actually can become on-shell, and propagators become in on-shell, meaning that the transition matrix element will become infinite. That singularity is cancelled between similar types of singularities in the loop integrals in virtual corrections. Again here, and if you're right here, you see this propagator can become on-shell in the real, this other propagator in the complex conjugate amplitude can become on-shell, whereas you have two propagators in the matrix in the virtual correction here, two Fermi propagators can also become on-shell. So what happens is that the singularities, infrared singularities of real emission diagrams actually cancels between different multiplicities, between different number of particles in the final states. Simply being a reminder of the fact that the particle number operator in perturbative quantum field theory is ill-defined. It has singularities, it doesn't make any sense. The same here. So you can't rely on counting the number of particles alone in order to get you a reasonable result for a fixed coupling power. You need to include virtual corrections. The result, when you do that, when you include both virtual corrections and sort of kind of these real emission corrections, where you radiate where you include another particle in the final state, are inclusive cross sections, and measurements that ensure that cancellation of singularities occurs are called infrared safe infrared safe measurements. And the theorem that proves that the cancellation of singularities does occur for infrared safe measurements is called the Kinoshita-Lee-Naunberg theorem, or KLM theorem. However, once you include virtual corrections, you step into another whole big mess. Virtual corrections include loop integration. Loop integration is an integration, so typically you would assume, given that what I've told you right now, this might be something that you would want to perform numerically. However, that's not what we do typically. We actually perform these integrals beforehand on paper, and then try to map these integrals onto simple integrals that we can perform on paper, called master integrals, after a lot of algebra, and then use these master integrals to assemble the result of the loop integration. And one of the reasons for that is efficiency, which because once you have pre-calculated something, it's always kind of most efficient, easy to use. And the other part is, of course, that the final state itself does not change due to loop integration. So there is really no need, in a sense, to keep track of the loop integral points individually. Though still, mapping these integrals onto master integrals is a tough problem, so you have to be clever about it. And typically, that cleverness comes from fields outside of Monte Carlo event generators. So there's a whole bunch of people who try to sort of be clever about mapping integrals to master integrals. The more or less simplest, the more or less gist of it is that the integrants that you integrate are polynomials of the momenta divided by monomials, simple monomials of momenta, meaning kind of divided by some propagators that are just squares of momenta, relatively easy. So what you do is you add and subtract simple functions to these integrants in order to cancel some of these numerators, make the numerators kind of more easy. Then find for the more easier integrants, find these master integrals, and then you are left with sort of a big mess of a leftover that is kind of all the things that you added, subtracted out again, and the initial integrand. But you have created a lot of different equations by adding, subtracting things in numerous ways. So now you can actually sort of look at the system of equations and try to solve That's system equations for the last remaining bits that you don't understand by, for example, Gaussian elimination. So here, we don't do things numerically, we do things algebraically. Or loop providers or clever people like in Reduce and Fire and so on do these things beforehand algebraically. So more or less, this is solved at one loop, though. At two loop, things are still quite complicated, and which is also one of the bottlenecks why we don't have really sort of complete general next to next leading order event generators yet. Okay, so I'm actually a bit ahead of time, I think, which is good, given that I kind of wasted some of your time, sort of used up more of your time in the first lecture. So let's go back to infrared singularities, because that's going to be very important for the upcoming lectures. Infrared singularities in these multi-parton amplitudes, where multi-parton means, for example, you have additional gluons, photons, whatever in the final state. These singularities have a profound consequence. Nature will attempt to dress outgoing states in as many partons as possible in order to take advantage of that enhancement. So your asymptotic states of your scattering are not individual particles. They are particles with a whole cloud of particles that are distributed such that such that you make these enhancements, you take advantage of these enhancements as much as possible. Which means, for example, that the partons that accompany, or the particles that accompany the hard scattering particles will be very collinear, close in angle to the original particles, and they will be very low energy, because that really takes advantage of the whole enhancement as much as possible. And nature will do exactly that. So in this diagram here, for which the cross-section is given again by the phase space integral over the transition probability and the flux factor, I've now written out the flux factor, which is basically just the velocity of the initial incoming particles here. I've written this out explicitly just to show you how this actually factorizes a bit. So imagine now that this gluon that you radiate with momentum k starts having a very small transverse momentum relative to this line. So its angle and energy are becoming small. Kind of the energy becomes small, the angle relative to this line becomes small. So small pt, transverse momentum, and in this case, we can approximate the energy of this intermediate form momentum as z times the energy, some fraction between 0 and 1, z times the energy of this incoming particle here. This means that this intermediate particle here is almost on shell, meaning that the propagator here can be replaced by, well, 1 over pa squared, which is roughly p minus k, and a polarization sum in the numerator. Rather than p slash minus k slash, you can approximate this by the polarization sum. Now, the polarization sum effectively means that there is now a matrix element contracting u and u bar out here, followed by a matrix element that contracts u and v bar here. So already this polarization sum, using this polarization sum, factorizes the matrix element into this emission blob and all the rest. Similarly, for phase space, you can also factorize phase space in this limit into a two-body phase space for producing these two particles, and 3 more variables that are relating to the emitted gluon: the angle, azimuthal angle, this energy fraction z between 0 and 1, and the transverse momentum of the gluon. Note that what would happen is that this factorization of the matrix of the phase space introduces a denominator 1 minus the energy fraction. So that means if this gluon here becomes exceedingly small energy, then this intermediate particle here actually has almost all of the energy of the original incoming particle. So Z is close to 1, and this whole phase space measure diverges. Finally, the flux factor itself, again, also factorizes into an energy fraction times the flux factor of this whole, this diagram, where this line is assumed to be the particle that had been extracted from the beam previously. That means that all components of the cross-section factorize: the flux factor, the matrix element squared, and the phase space, meaning that the total cross-section itself factorize for producing these 3 particles, factorizes into cross-section for producing 2 particles, and the integral over a universal function that determines this decay. This is called a splitting function, and I will call it P. Very typically, it will not depend much on the azimuthal angle or the transverse momentum. So quite often we'll see P of Z, for example, when looking at the strictly collinear limit, where the PT of the gluon becomes very small, whereas its energy can remain large. Then these P's, for example, are what are known as the Dieglab or Dockschitzer, Krivov, Alterelli, Parisi splitting functions for gluon emission. These splitting functions contain all the singularities of this diagram. There's a finite diagram that gives us a finite cross-section d sigma 2, and all the singularities are factored into this little bit here. With that, we finally are at a stage where we can actually write down a meaningful way of calculating a cross-section that includes virtual corrections and additional particles in the final state. The way how this will work is you take a diagram that contains additional emissions in the final state. You subtract from it all their singularities and add the thing that you've subtracted back to the virtual corrections, which you know should contain the same types of singularities in a manner such that they would cancel the real emission singularities. This is what I've tried to do here. So once the divergences are factorized, we can attempt to calculate an observable at next to leading order accuracy, meaning including one loop corrections and a single additional particle in the final state. We can calculate by saying, now our measurement will indeed will be approximated by a more complicated expression, which includes a tree-level differential scattering cross-section, the virtual correction to that, the correction with an additional final state particle, n+1 particles in the final state, and a subtraction in order to render this integral here, or this bracket, finite, which you then have to add back naturally in order so that you have only added a net 0. You add it back to the virtual corrections, and you know that these things again are finite, because otherwise, because the virtual corrections themselves should have had the same singularities as the real corrections, meaning that the virtual corrections also should have the same singularities as the approximate real corrections, that is approximated by only the most singular components. Just a quick second, and I'll get back to you. Right. Again, this is a way of just enforcing the Kinoshita-Lee-Naumburg theorem. Note, however, there's one subtlety that I haven't told you, which is in the real corrections, which contain an additional particle, your integral is over a higher dimensional phase space, and your test function, your observable, should also depend on that higher dimensional phase space. So that means that these real corrections produce a slightly different value for the observable than the virtual corrections or the tree level corrections do, which only still contain n particles. But when we subtract and add, we have to subtract and add the same thing, including also the same test function, the same observable. This is why you see that there is a mismatch between the dependence of this integral on the test observable in the real corrections and their subtractions, because it cannot do the subtraction in this n+1 body with n+1 body dependence, because then we couldn't add it to the virtuals. Whew. However, it still allows you to create a numerically stable prediction for observables for which when you are approaching the limit where the real emissions diverge, the observable with n+1 body dependence will actually default back, will be degenerate with the observable with only n body dependence. Again, this is the definition of an infrared safe observable. For an infrared safe observable, in the limit where the infrared singularities occur, the observable will again will go back to looking like a tree level like observable, and this bracket here will be finite. Finally, however, what it doesn't allow you to do, and what we'll do in the next lecture, is to actually allow you to generate events. Because now you have events that have, or you have phase space points that have n body dependence, you have phase space points that have n+1 body dependence, and these different phase space points, these different events are correlated with each other in such a way that if you do anything to them, you might break this correlation and might break the cancellation of singularities. So how to fix that is what we'll also do we'll do towards the middle of the next lecture. And now, Rock, I'm sorry I kind of kept you waiting. Ask your question.
No worries at all, thanks. But I think I've already gotten the answer myself. I was just a bit confused because we're still writing d phi n as an n-body phase space, but the calculation is at next to leading order.
Mm-hmm.
So you might have meant just an order above n particles, I suppose.
Right. So indeed, so n here is the index of, or is the number of final state particles, and that doesn't change by virtual correction. So this is why you put it in that kind of bucket up here, but it would change by real correction because you have an additional, say, gluon or so in the final state. So you'd put it in that bucket.
Indeed, thanks.
So with that, I'm actually done early, 5 minutes early, so we have plenty of time for questions.
Yes, perfect. Thanks a lot, Stefan. So I didn't see any questions in the chat so far, so everyone feel free to shout directly at Stefan with any of your questions.
I might have a question. Hi, Stefan.
Hi, Mace.
So on your slide 31, maybe you can go back there.
Yep.
I was thinking it's maybe a bit naive, but the G1 plus G2, you expect them to be an overestimate of the function of the thing you actually want to sample of F. But what if the interference of these two things are destructive?
Yeah.
Is
indeed.
there a chance that it's smaller than F, or?
So what you so what I meant to write here is in a sense that so G is this guy squared, G2 is the other guy squared, and then I actually don't add. So then you kind of multiply them with some factors in order to make sure that this is always larger than these two sums plus the interference. So that not that this first line is identical to the second line. Only that kind of this first line you write as if it looks like this. I should have had actually a smaller equal here. I think that would have been kind of more clear. Now it's you touch on a good point in the sense that the interferences of these two diagrams actually have both of these singularity structures in them, right? So they have a structure where that the interferences will become large, both when this intermediate particle becomes on-shell and when this intermediate particle becomes on-shell. So these are not as easily factorized as these kind of individual pieces. So trying to find multi-channel and multi-channel integrator that kind of can try to track also these sort of sub-leading or more entangled singularities is typically very challenging, very challenging. If really needed, you do it on a case-by-case basis. By basically you adjust G1 and G2, and you maybe introduce even a G3 in order to sort of see which one you would want to use.
I see. Thank you.
Yeah, but interferences are always tough. In particular, if they change sign, then of course it becomes difficult to have something good, find a good definition of what you mean by probability.
Hi, I have a question.
Go ahead.
On slide 35.
All right. Velocity amplitudes. Great.
Yeah, the last diagrams. So I mean the one with 3 and 4 in green, and the one with the 3 and 4 in blue, and 1 and 2 joining. Are they supposed to be the same diagram, like two different versions of the same diagram?
No, indeed not. But so the way how you sort of think about it is you start from the outside with extremely simple, like say spinors, wave functions, polarization vectors, and you contract them in all possible manners in order to create all possible diagrams. So these two diagrams would actually be different, and even worse, if you want, these two diagrams have different singularity structures. Because in this case here, for example, on this right side, right, things can become singular if if this propagator becomes on-shell, or if this propagator comes on-shell. Whereas here you have slightly different propagators that might become on-shell. So, for example, it can be quite useful actually for phase-space generation to know how you've contracted these things in order to decide how you want to insert additional integrations into your phase space in order to factorize it into smaller pieces.
Okay.
But these are definitely, this will absolutely produce different diagrams, which is kind of what you want, because you don't want to write down the diagrams yourself, each individual one, because you might forget one. So this is kind of in this way, you simply, for each helicity, you create all of them.
Okay, thanks.
Happy to help.
Very good. So already triggered quite a few questions. Are there any more that we want to discuss now? Otherwise, as we said, there will be plenty of opportunity to discuss further, also in smaller groups, and with Stefan floating around the groups and answering questions here and there later in the evening. But if anyone has anything urgent on their mind, then it's probably a minute left to ask now. There's a question in the chat. Wouldn't the Feynman rules in the theory restrict the possible contractions? Is the question.
Oh yeah, absolutely. So in a sense, you're still, kind of your sort of way how you do contractions is still informed by your Feynman rules. And you might even sort of, by the way of in inspecting certain kind of subsets of Feynman diagrams, come up with sort of a more specialized Feynman rules for larger parts of a whole diagram, for example, in order to make your life easier. And that is exactly where this whole kind of field of finding an efficient method in order to contract these comes in. You can have effective Feynman rules in order to make your life easier and more efficient. In this case, even. Yeah.
Yes, the art of making matrix element generators efficient, especially with recursion relations, is a very comprehensive art.
Yeah.
So I don't see any further questions right now, neither in the chat nor any hands raised. So I think this is the end of our morning session. Thank you very much, Stefan, for this super nice introduction already to Monte Carlo principles. So we'll hear more from the Monte Carlo side tomorrow in the morning, and more from specifically the QCD side, which is of course featuring a lot in the Monte Carlo event generators as well. So we'll hear a lot about the QCD side in the afternoon session. I will stop the recording now, and we will upload those videos later on such that you can view them. It always takes a little bit of time for Zoom to process those recordings, so they won't be available instantaneously, unfortunately, but we hope to make them available as quickly as possible. Hopefully, at least the morning session sometime in the early afternoon, so that you can view them after the afternoon session. Or not you, but anyone else, or if you wanted to look something up again before the recitation session. Cool. Thanks a lot, Stefan, and everyone for connecting, and see you hopefully in the afternoon and or in the evening.
Yeah.
Bye-bye.
See you at the latest tonight. Bye.
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 Bye. Ciao.